And I may have to back up a little bit and pick up where I was going when I brought up Mr. Ampere's name. Mr. Ampere came up with an interesting experiment. He had a voltage source, and he set up something like this. So here's a plus and a minus, and current's flowing through essentially a short circuit. It's not really zero resistance, there's always some resistance, but there's a lot of current because there's a low resistance, he had wire there. But he had a generator, something that could generate the current at the levels that would make this process happen. What he noticed is, these wires are attracted to each other. They tended to pull toward each other. You can see them bending. Ooh, what made that happen? A guy named Michael Faraday, after which the term farad, remember capacitors are measured in farads, and that's abbreviated F, and it's a big, big value. So most capacitors are micro, meaning millions of a farad, or less. They're sometimes microfarads or picofarads, 10 to the minus 12. Very small numbers because farad is huge. A farad capacitor would be, bigger than iron. That's big. And what Faraday figured out is that the reason for what Ampere discovered is that there is a magnetic field flowing around a conductor when there is current flowing through a conductor. So if there's I here, there's H here. There's even a rule for which direction the flow is by convention. If your thumb, if you use the right-hand rule, the thumb points where the current does, your fingers point the direction the magnetic field flows around the wire. And that's why the electric motor works. You put current in a coil around the motor, you get a magnetic field. The magnetic field fed to the outer winding called the stator because it's stationary. And also to the part in the middle, we call it the armature, but we tend to call it more often the rotor because it's rotating. The magnetic field from the stator and the magnetic field from the rotor affect each other and they make the shaft turn. And that's how a motor works. A generator works the same way. A motor and a generator are really in the same box. The difference is if you turn the rotor and you feed current into it, you'll generate electricity in the stator winding. What if you don't want to feed current to it? Well, you put a permanent magnet in the part that rotates and spin it around, and you will get a current generated in the stator winding. If you plug current into it, it will rotate. If you rotate it, it will generate current. Perfectly equal and opposite. And if there was any doubt about that, when I took an electric machinery course in college, we had these things called motors, or generators, or which. They were both the same. We had a motor and a generator connected to each other on the same shaft. You put current on one, you turn the other generated electricity, this one used electricity. It's the same winding, same everything. You have to wire it up properly to make it happen, but they're the same animal. Okay, so Michael Faraday used this principle that current flowing through a wire will make a magnetic field appear. What you have with this coil, which I spoke of, this inductor as I would call it, is you put another and another and another winding, and each one produces its own field, and they all add up and you get a bigger field. The more times you wrap the wire around the coil form, you can produce a coil. So if you want a bigger magnet, more windings. The turns that you have determine the strength of the magnetic field. When they build a transformer, the voltage in to one winding produces a coupling by the magnetic field to the secondary winding, and the turns ratio, how many turns of wire you have here versus how many turns here. If there's 10 times as many turns here as you have here, you put 120 volts here, the turns ratio will determine the voltage out. So you put 120 volts in, you get 12 out. If you have 10 times as many turns here as you have turns there. Well, it sounds like a cheap way to make high and low voltage. There's a trade-off. Power is voltage times current. If you want your voltage to change, your current's going to change correspondingly. So if you turn the voltage up, you're going to get less current. You get the same power though. Power is energy per unit of time. Energy is the part you can't destroy or create. You have to kind of preserve it. Okay? So there's no 2 horsepower perpetual motion machine in the universe. This thing all fits the laws of nature, and everything here is going to be easily appreciated to be kind of consistent with anything you may have learned in science in your life before this. One other nice thing about electricity and electronics and radio and all these things that we're talking about in these sessions is they are metric. The whole world uses the same exact terminology. We call it volts, so do the Europeans, so do the Asians. Why? Metric is the universal terminology. We, in America, have not quite gotten with the program. We're still using the English system, even though the Brits are pretty much more into metric than we are. It's kind of hard to change an industry that's got a gazillion years of experience. How do you go to the hardware store and buy anything but a 2x4? Or get a sheet of plywood that's anything but 4x8 feet?
We were supposed to go metric in '78. What happened?
No, the industry fought it, and the decimal inch, in other words, they chopped the inch into hundredths or thousandths so that you could have a decimal, which tends to mimic the metric idea, but the basic unit of measure is still, unfortunately, cubits or
So
foot.
even on Japanese and European automotives, though, they will use standard size bolts these days because they fall in between the readings that they need for, the strength of that particular bolt. And
Well, if you buy a General Motors car, I guarantee you, if you want to change the oil, you're not going to use a 5/8 inch wrench. Like
And
you
the
will
other
on a
way.
Ford or Chrysler, you'll end up using a 15 millimeter wrench. I've done it enough times to know. GM got with the program. The other car companies are other American car companies haven't quite yet. But now that Fiat owns Chrysler, maybe they'll change that. And only Ford's just going to have to figure it out for themselves. But I have a feeling they will. There comes a point where there's so much stuff that's metric anyway. I buy power supplies from a company called Meanwell. They're made in Taiwan. And I have to put M3 screws in, not 4, 6, or 8. Number 4, number 6, or number 8 screws like we would in the States. So you have to have a little bit of each in your toolbox. Question?
I'm a machinist, and you cannot buy metric steel. That's the biggest crux right now.
What, the dimensions of the steel or the...
The sizes, they don't make it in metrics.
Okay, because when you buy steel, it's like 10-20, talking about the carbide
Oh,
ratio.
no,
That's the
I'm talking
metallurgy.
physical
So
size.
you're talking about the physical side. If you're buying a rod
I
or
can put
bar
a metric
stack.
screw in,
Okay.
but when I go buy the material,
You're gonna-
until they change that, it'll never flip.
It's like the railroads. So what is it?
It'll never flip.
4 feet, 3 7/8. I forgot what the dimension is, but the spacing between railroad tracks dates back to the Romans. That's the spacing between the chariot wheels. And the Brits got it from them, and it just kept going. Nobody wanted to change it. So here we are. Even though, as kids, we had HO gauge trains, which were metric, and then Lionel used the old edge system. It'll change. Come on, we had cameras that were 16 and 8 millimeter film. If you had a 4x4 film format, or 6x6 was 120, 620 film. That's 6x6 centimeters. They decided in the film industry they were going to go metric sooner than everybody else did. Go to the jewelry store and you want to buy an 8 millimeter ring for your sweetie. Some people have gotten it, but others just haven't. Magnets. Here's the interesting thing. What Faraday figured out is when the current flows, you get a magnetic field. Now here's a cute little experiment that he did along the way. I think he did, I think Amper did this first. They took a bar magnet. So you got this magnetic field going around it, because you got a north pole and a south pole of this thing. Then you got this little meter. They call it a galvanometer because it measures small currents. All meters measure current, even if you have a voltmeter, it measures current. We'll talk about that in this course because I will show you how a meter works. An ammeter has a galvanometer in parallel with a shunt, a low impedance bus bar that conducts at very low impedance. A voltmeter has a high impedance series resistance. Either way, they do it so that a small current will flow through the meter and the rest of it will either go, if you're measuring current through the bus bar, or measuring voltage will be cut down by the resistance. All right, so here's this magnetic field around the magnet, and here's this meter. And the meter normally will stick straight up in the air. It's got zero off, and if the current flows one way, it'll deflect accordingly. If it flows the other way, it'll deflect accordingly. So when this coil was moved, there was a deflection one way. When it was moved the opposite direction, there was a deflection the other way. When the conductor went through the magnetic field, a current flowed. Remember what I said about Faraday and his electric motor? Generators and motors are the same thing. If you put a current in, you're going to get a magnetic field out, and you're going to make it into a motor. If you turn the thing, you're going to get a current out because you have a moving magnetic field. So whenever a conductor crosses a magnetic line of flux, you get a current flow. Whenever you have a current flow, you get a magnetic line of flux. Equal and opposite conditions. And the formulation for that, I will write down, and you'll say, I don't want to see calculus. You're going to get some right now. The integral of d phi dt is equal to minus v. The voltage you get is the summation of all the changes in flux. V is flux per unit of time. That's d phi dt is calculus for differentiation, meaning the rate at which something changes. The integral sign says the summation of all these little changes added together. That's what that fast back S is, of course. So this change of magnetic flux per unit of time produces a voltage. What about that minus sign? It has a very significant reason for being there. I'll show you that in a sec. That thing is called Faraday's law. It is the second of four equations that electrical engineers have to deal with, especially if they get into very serious things like antenna construction, called the Maxwell's equations. And Maxwell's equations are all vector math, and they are just ugly looking things, but they're also ugly to deal with too, because you deal with terminologies you'll never see anywhere else in physics, called curl, divergence, gradient. There's a whole course called Engineering Electromagnetics that I took, and I said that's got to be the hardest course I'm ever going to see, because I can't even conceptualize this thing until toward the end, when I finally went over it enough times I could understand how to solve these equations. But that one was pretty simple. Faraday's law really says, very simply, move the conductor through a magnetic field, you're going to get a current flow. Put a current through a wire, you're going to get a magnetic field. How convenient is that? Okay, so here's the same thing as that correct diagram. Here's plus, here's minus, there's a current flow, and when you get a current flow, you're going to get a magnetic field, but the magnetic field isn't all at once. It's just like when the capacitor builds up. The magnetic field grows like that, exponentially. That's actually some natural logarithm base times some value of x that determines the shape of that curve. That means that while you're putting current through the wire and the magnetic field is expanding, the magnetic field expanding is producing a current. I know that you don't think about it that way, but this is the experience. You put a current here, you get a magnetic field that starts out small and grows. As it grows and it crosses through the conductors, it produces a current flow opposite the direction of the current that started the whole process. That reaction is called Lenz's law. It is the reason why there's an impedance when you feed alternating current to an inductor. Because what you're doing with an alternating current, just like you did before, you turn on the juice, and the current this time, not the voltage, but the current builds up to some maximum amount. And when it does, nothing changes. It stays that way unless you reverse the voltage in this. You know, this was plus before, it now becomes minus, this becomes plus, and then the same thing as before. It goes back to zero and then goes the other direction. So when you are putting an alternating current here, this magnetic field is growing and then shrinking, and then growing and shrinking, growing and shrinking, and in doing so produces an opposite voltage, the one that started the whole process. And that's the significance of the minus V, and that is why feeding alternating current to an inductor will increase the impedance that it presents to the circuit. Those are equal and opposite characteristics. When this thing alternates faster, it conducts better. When this thing alternates faster, it conducts less. You put direct current through this, it's like it's not there. You put direct current through this, it's like an open circuit. Nothing goes through. Oh, we're in a fire station, by the way, so when they dispatch a fire truck, you get to hear the announcement of where the guys are going.
Engine 11, at 11:49, 1013 Field Road, stroke, code 1, Zone 11, engine 11, at 11:49.
Trying to figure out if I know where the house is.
Field Road, stroke.
Sorry, hasta la vista.
Yeah. Run out.
The weenie, yeah, that weenie roaster.